Alrighty, so this is going to be the problem solving session for section 6.2. I'm going to pick a couple problems that are similar to the ones in WebAssign. They shouldn't be any of the numbers that you guys get, but it'll give you an idea of how to do a couple of the ones that I think you guys might have trouble with. Just because, not that they're super difficult, just that there's some mathematical things you need to know that are easy to forget. Okay, so the first one we're going to do is find the volume of the solid obtained by rotating the region bounded by y is equal to ln of x, y is equal to 1, y is equal to 2, x is equal to 0 about the y-axis. Okay, so just kind of if you've forgotten everything we've talked about, what we're trying to do is we're trying to write volume as an integral from a to b of some cross-sectional area times dx, or a to b a dy. It just depends on which direction the thickness in your whatever object you're using to do the area with is going, and you'll see what I mean by that in a second. Okay, so let's draw this. So you have to remember what the graph of ln of x looks like. Looks something like this. This is 1. Here we have y equals 1. Here we have y equals 2. So we're going to have something looks like this. And so the y-axis is the line x equals 0. So the area I'm interested in is going to be this one after I rotated about the y-axis. I didn't give myself a lot of room to do that. But so, let me just re-erase that and draw it real quick. I can do this quickly. So really the area that I'm interested in is this one. And then going to get something similar looking when I rotate it about the y-axis. So this right-hand side was the original area. Then I rotated it around to get the other area. Undo all those green things. Now I want to find the volume of this. I want to find the volume of this region here. And so the question becomes, okay, what do I want to use to represent my area here? Do I want to use discs? Do I want to use washers? Do I want to use some other shape that I can find the volume of? And here, if you look at a cross section, so if you look at a cross section on this thing, I get cross sections of circles. So I can extend those by like a small, width here, and I get cylinders. So I'm going to use discs to do my approximation. Sorry, to do my integral. It's not an approximation. When you do the integral, you do get the exact area. Just these approximating discs are how you think about how to set this all up. Okay, so let me label. So this was y is equal to ln of x. This line right here was y is equal to 1. And then this line up here was y is equal to 2. So I'm just drawing all my stuff. Okay, so what we're going to do is we're going to use discs. So the area of the disc is pi r squared then. So I need to figure out my radius. My radius I'm going to highlight here is going to be, that amount of that distance there. And you ask yourself, okay, what can I use to represent that distance? Well, I can use the x coordinate of, wherever I'm at. So I can write this as pi x squared. And now I ask myself, okay, what then is the volume? Well, volume is going to be integral area, and do I use dx or dy in this case? And the answer is, because my because my disk, extends into the y direction, the thickness of it goes in the y direction, I'm going to use dy. So the way another mnemonic of that is, you can imagine this having some tiny thickness dy that is extending in the y direction. So my volume then is going to be the integral of the area times dy. So now we have our first problem. Also, I'm going to integrate from a to b. We'll talk about what a and b are when we figure out as we go through the problem. So what you'll notice now is, my integration variable, so my differential down here is dy, and my area is in terms of x, which I cannot do. I cannot integrate x dy. It doesn't make it's not something you can really figure out without putting x in terms of y first. So because my differential is dy here, I want to determine x in terms of y. And so when I do that, the way I'm going to do that is if I look at my graph here. So, if the point is given by x here, I'm sitting on the line y is equal to ln of x here. So I'm sitting on the line y is equal to ln of x. So the idea is, I can solve this for x. And to do that, you'll remember I need to exponentiate. I need to turn both sides into exponents. So what I'm going to do is I'm going to write e to the y then is equal to e to the ln of x. And you'll remember, the reason I do that is because e and ln undo each other. So I'm going to get e to the y is equal to the natural log of x. Sorry, they undo each other, is what I said. So e to the y is equal to x, and that tells me what x is. So what I'm going to do now is I'm going to plug this into my volume. Sorry, into my area. Area then, which was given up there by pi x squared. Now I know x is e to the y, so this is going to be pi times e to the y squared. E to the y squared is e to the y times e to the y, or e to the 2y. And now I can set up my integral. So I have the integral from a to b, which is going to be the volume, of pi x squared, so pi e to the 2y, dy. Now I need to figure out my bounds. So to figure out my bounds, I'm going to look back at the figure. So I'm integrating with respect to y, and you can see, okay, where do I start in terms of y? Well, I start at y equals 1. I start on that line. And I end at the line y equals 2. And that tells me, that just gives me directly what my bounds are. So this is going to be the integral from 1 to 2 pi e to the 2y dy. Now we can just do this integral. So pull the pi out. Pi e to the 2y dy. If you're not comfortable with it yet, you can do a use. So if you're not comfortable doing that one quickly, you can do a use substitution. So I'm going to do it just for the sake of people can see all my steps. So you could let u equal 2y, and then du will be 2 dy. So dy is 1/2 du. And when you do this, you also need to change the bounds on your integral. So u of y is 2y. So plug in your bounds. I get u of 1 is equal to 2. U of 2 is equal to 4. I'm going to replace my bounds with those numbers. So this is pi times the integral from 2 to 4. E to the 2y is now u. dy is 1/2 du. And I'm just going to plug this in. So this is pi over 2, factor out the 2. Integral from 2 to 4, e to the u du. Integral e to the u we can do. It's e to the u. I'm going to evaluate between 2 and 4. So this is pi over 2 times e to the 4 minus e to the 2. And that'll be my final answer there. So again, you don't have to do a u substitution here. If you're, you can see that the integral of e to the 2y is 1/2 e to the 2y. That's fine. It's a little easier. I just wanted to write out every step so everybody sees it. You'll get the same answer no matter what. So I'm gonna stop that problem there. I'm gonna not stop the recording though, because with these, I'm just gonna get 2 problems done here, and not worry about the length. With the lectures, I'm trying to keep them a little shorter, because it's easier for you guys. But now I'm gonna do a problem in the book. So this is 6.2.14. It's also similar to a WebAssign problem. So we have find the volume of the solid obtained by rotating the region bounded by y is equal to sine x, y is equal to cosine of x, x is between 0 and pi over 4, about y is equal to -1. Okay, so this is one of those problems that you really have to be careful about drawing, just so you know everything's correct. So I'm going to go ahead and draw our axis of rotation. So we're going to do it at -1. So this is going to be our axis of rotation. And then let's go ahead and draw sine of x. So sine of x is going to look, so at pi over, so we're going to pi over 4 is the idea. So pi over 4, let's call this 1 over square root of 2 here. Let's call this 1. So sine's going to look something like this. Cosine's going to look something like this. And that's going to be, the shape that we rotate around this axis down here. So when I do that, and I'm really bad at this, we're going to get something that looks like maybe something like this. And then a little more symmetric than that, but it's the best I can do. So they're supposed to be the same, length on both sides. Maybe I can do a little better. So it's supposed to go out to pi over 4. That's a little better. All right. So, okay. So again, the premise of these problems is we're trying to find volume as an integral from a to b, a dx or dy. In this case, I'm going to write dx because I already know which direction I'm going to integrate in. But again, you need to make sure, this isn't a general formula. It's either dx or dy. But okay, so let's figure out our shape here. So if I imagine a cross section, taking this and slicing through, I'm going to get something that looks like this. And if I do it here, cross section is going to look like this. And you can see, whatever the cross section is, has a big hole in it. So that kind of hints that it's we're going to use washers. So you'll need to remember the area of the washer is going to be pi times the outer radius squared minus the inner radius squared. And now we need to determine what the outer radius and the inner radius are. So if I look back up at my drawing here, you have to be careful. So you have to also think about, what am I trying to measure it from? So looking at, these big washer, the big red lines here that I've just drawn an arrow to in green. So the radius I'm interested in is, the radius from the center of rotation, the axis of rotation, sorry. So I'm interested in figuring out what that length is. And this will be my R inner. And for R outer, let me pick a different color just so. My radius will be that. So this is R out. And so that kind of gives you an idea of how to determine R out and R in. So R out then so, I can figure out what this point is that I've just, so I guess I can use the highlighter. I can figure out what that point is there. Figure out what the height from the x-axis is of that point because I know that this line here is cosine x. And so, so in order to, so that gives me, the distance from the point here down to the x-axis. So that gives me that distance, just doing cosine x. I also need to add 1 to that because I also need to take into account that there's also a distance of 1 between the x-axis and the axis of rotation. So let me go through that one more time. Let's see if I can erase this highlight. It's not working very well. Actually, I know why. Nope, that is definitely not working. Okay. So one more time. I know that the height here is given by cosine of x. And by height, I mean this height. So this height is cosine of x that I'm highlighting. But I don't want just that height. I need cosine of x plus this distance here. And this distance is 1, because remember, distances are positive. So my R outer then is going to be cosine of x plus 1. And R in, similarly, if you look at the curve down there is sine, that's going to be sine of x plus 1. Now I'm going to plug that in. So the area of my washer then is going to be pi. The outer radius squared, so outer was cosine of x plus 1 squared minus sine of x plus 1 squared. This is going to be pi times cosine squared of x plus 2 cosine of x plus 1 minus sine squared of x minus 2 sine of x. All of these get minus signs because there was the minus sign here that I just highlighted. And let's simplify just to get as far as we can go. This is pi cosine squared of x minus sine squared of x plus 2 cosine of x minus 2 sine of x. So I'm going to leave it here, though. So this does most of the hard work. The last part to this, and it's the same on your guys' problems, you're going to need the identity. So we talk about this in the trigonometry stuff. Cosine squared of x, in order to integrate that, we write it as 1/2, 1 plus cosine of 2x. And then sine squared of x is 1/2, 1 minus cosine of 2x. And from there, you can do the integrations. It's not too terrible. It's just, again, that's going to take me way too much time. And that's your guys' job anyways. So the last thing I'll say is, what are the bounds? So this one's a little simpler to do. So if I look, what x values do I go through? I start at 0 here. I end at pi over 4. So I'm going to get the integral from 0 to pi over 4 a dx. I'm going to stop there. Again, this integral it's very doable. It's just tedious. And you guys need the practice anyway. So if you have questions about it, email me. And I'll stop here.